Hello everyone, welcome back to another interesting episode of All About Bridge Engineering, where I intend to bridge the gaps between books and reality and change the way we are taught things in our professional courses, whether in India or at any university across the globe. So this episode will be focusing on the practical implications and the real life application of a cantilever beam in structures around us, particularly in bridges around us. So you will be amazed to know that this basic knowledge of analyzing a cantilever beam is not only utilized in designing one component of the entire bridge, but at least three very important components of a single bridge. So without wasting further time, let's straight away kick off with the main content of the episode by starting component number 1, which you can see is a pier cap. So notice that this pier cap is supporting three pedestals over which this entire superstructure is rested. So the first and the foremost load for which this pier cap has to be checked is its own self-weight. Notice that this is not a prismatic section, as it is tapering from the root to the tip and hence has to be analyzed as if a single cantilever beam is subjected to a uniformly varying load with maximum intensity as the root and minimum intensity at its tip. Second load for which it has to be analyzed is the dead load reactions and the live load reactions and all the vertical reactions which are brought to it through this pedestal at the edge, and it is analyzed as if a cantilever beam with this span is loaded with a single concentrated load, the sum of which is equivalent to the dead load plus live load reactions of the traffic moving above. So these two are the basic forces for which this cantilever type pier cap has to be checked, and accordingly it is designed. Another force for which this cantilever pier cap is checked is a torsion. So you may be wondering how torsion can be introduced in this system. So please note that even if the spans on both the sides are equal, there are high chances that the traffic movement at left span may be different than the traffic movement at the right span, or the traffic at the left span is fully loaded or one of the spans is partially loaded. So based on the reactions difference of the live load on the individual spans, some torsion may be generated, and that torsion is converted into equivalent bending moment and equivalent shear force, and that is added to the main bending moment and main shear force for designing the cantilever beam. So this was one component which is designed as a cantilever beam in bridge structures. Another two components that I will bring to your notice are a little difficult to figure out, and only the professionals who are involved in bridge designing can correlate very well, but still I will discuss it. So second component for which the bridge is analyzed as a cantilever beam is a dirt wall. So first let's discuss what a dirt wall is. So this is basically the abutment cap, this is the transverse seismic arrestor, and this vertical member that you are seeing is basically the dirt wall, which is not clear in this structure because it is already constructed, but still by this sketch you can visualize that this dirt wall is supporting earth behind it, over which an approach slab is supposed to be rested, and this dirt wall is subjected to horizontal earth pressure, and it is acting as a cantilever in the vertical plane. Normally in all textbooks we encounter cantilevers lying straight, lying in a horizontal plane, but this dirt wall is a cantilever lying in a vertical plane, and hence it is designed for earth's pressure forces which are lateral in nature, as well as live load surcharge which is added to the earth pressure forces, and to add more forces, some braking forces due to the moving traffic are also applied at the tip, and although they are subjected to a very minimum vertical force due to the moving live load traffic, but that can be ignored because the component of horizontal lateral forces due to earth pressure, due to braking and due to the live load surcharge are predominant than the vertical force. So this was component number 2. So now let's move to the component number 3, which is again designed as a cantilever beam in the bridge structure. So you must by now would have got an idea that how important is the analysis of a cantilever beam, which is one of the basic determinate structures which every civil engineering graduate comes across through his degree courses. So now just have a look at this pier. This is a circular pier. I suppose it is rested on an isolated footing, and if it is resting on an isolated footing, so it may be subjected to a base pressure for which it needs to be designed. So notice that in the longitudinal direction, apart from the vertical forces through which the base pressure diagram will be a uniformly distributed load acting upwards, it is also subjected to some lateral moment in the longitudinal direction and as well as in the transverse direction, but we will restrict our discussion to the longitudinal direction in this video just to limit the entire length of the video, but similar concept is applied to the transverse direction as well. So just focus how this longitudinal movement is developed simply because of the horizontal forces acting at different lever arms. Suppose first of all the main horizontal force is due to the braking forces acting on the pier, acting on the superstructure due to the live load movement. Secondly, longitudinal seismic forces which are calculated by seismic coefficient method by multiplying the base acceleration AH with the seismic weight of superstructure, seismic weight of pier cap, seismic weight of the substructure as well, and that is acting at their subsequent lever arms. That also induces a longitudinal movement. So if a longitudinal moment is also added to the already existing vertical force, you will notice that one tip of the base pressure diagram will be more stressed simply by using the concept of M upon section modulus, and hence a uniformly varying load is subjected to this footing, and for designing the footing, which section needs to be designed for the movement has to be very well directed. So first of all, you must be aware that if it is a circular pier, we have to convert it into an equivalent square section or equivalent rectangular section for determining the section where this moment has to be checked. And at that section, you will notice that this acts as primarily a cantilever beam. So notice that this simple theory of analyzing a cantilever beam subjected to various loadings like the concentrated loading, a uniformly distributed load, or a uniformly varying load, which is entirely covered in all solid mechanics or strength of materials textbooks, is utilized in designing the basic components of a complex bridge. So I just want to give you a super tip. If you are not good at analyzing these structures manually, start making use of readily and easily available softwares such as STAD or a SAP. You will find that these things are so interesting that you will develop that observation, that vision of how structures around us actually work. So this was all in this episode of All About Bridge Engineering. If you find the content relatable, make sure you hit the like button, subscribe to the channel, because I'm gonna bring a lot more things like this to enhance clarity amongst the grooming civil engineering students who are still in their final years, and it may help you in clearing certain interviews when you sit for the placements. So that is all. Till then, take care, stay safe, and just chill.